Welcome to this harbor beneath the stars. Wherever you are, let the sounds around you fade away. Together, let us lay down the clamor and weariness of the day, and turn our attention to the boundless, profound night sky above. Tonight we embark on a special journey, a cosmic voyage through time and space. You need no luggage, simply settle into your most comfortable position. Let your breath become steady and deep. Our journey begins in the familiar solar system, gradually sailing toward the edge of the Milky Way, until we reach the observable limits of the universe. Along the way, you may encounter astonishing truths, some sparking curiosity, others inviting quiet reflection. Yet all knowledge will ultimately dissolve into a lullaby for the soul. Now gently close your eyes. Imagine yourself floating in tranquil space, enveloped by gentle darkness, distant starlight guiding like a lighthouse. Let us begin with the stellar system that gave birth to us, embarking on this serene in the boundless void of the cosmos. The sun is our closest star. It has burned steadily for 4,600,000,000 years, providing light and warmth to the entire solar system. The sun was born from the gravitational collapse of a primordial nebula, a cloud containing dust and gas left behind by the explosions of earlier stars. Under its own gravity, the nebula began to spin and gradually collapse. The central material grew increasingly dense and hot, until the core's temperature and pressure reached a critical point. Hydrogen nuclei began undergoing nuclear fusion reactions, igniting a new star. This process spanned tens of millions of years, ultimately forming the sun we see today. The sun's core is a colossal nuclear fusion reactor. Every second, 600 million tons of hydrogen fuse into helium. Millions of tons of mass are converted into pure energy. This energy takes hundreds of thousands of years to travel from the core to the surface, where it radiates into space as light. The sun's surface is not uniformly bright. We observe dark regions called sunspots. These areas are slightly cooler than their surroundings, appearing dimmer. The number of sunspots follows an approximate 11-year cycle. This cycle is closely linked to solar magnetic activity. When magnetic field lines become entangled and reconnect, they release immense energy, triggering solar flares, or hurling vast quantities of charged particles into space as coronal mass ejections. The sun's outermost atmosphere is called the corona, where temperatures reach millions of degrees Celsius, far exceeding the surface's 6,000 degrees Celsius. This phenomenon is known as the coronal heating puzzle. Scientists continue to explore the underlying mechanisms. The corona constantly expands outward, forming the solar wind, a continuous stream of charged particles, blowing across the solar system at hundreds of kilometers per second. When the solar wind interacts with Earth's magnetic field, it produces the beautiful phenomenon of auroras. The sun's lifespan is approximately 10 billion years. It currently resides in its most stable phase as a main sequence star. In another 5 billion years, the hydrogen in its core will be depleted. The sun will begin expanding into a red giant, with a radius extending near Earth's orbit. Mercury and Venus will be engulfed. Earth's fate remains uncertain. Ultimately, its outer gases will gradually dissipate into a planetary nebula, while its core collapses into a white dwarf, slowly cooling over vast stretches of time to become a silent diamond in the cosmos. The 8 planets orbiting the Sun each possess unique environments and characteristics, together forming our diverse stellar system. Mercury, the innermost planet, is the smallest in the solar system, without atmospheric protection. Its surface temperature fluctuates dramatically between day and night. Daytime temperatures can reach 430 degrees Celsius, while nighttime plummets to minus 180 degrees Celsius. Mercury's surface is pockmarked with impact craters, recording billions of years of collisions with smaller celestial bodies. The largest impact basin is Caloris Basin, spanning approximately 1,500 kilometers in diameter and formed by a massive impact event. Venus, comparable in size to Earth, is often called Earth's sister planet, yet its environment is hellishly harsh. Its thick atmosphere, primarily composed of carbon dioxide, creates an extreme greenhouse effect. Surface temperatures remain around 460 degrees Celsius year-round, sufficient to melt lead and zinc. Sulfuric acid clouds blanket the entire planet, with atmospheric pressure 92 times that of Earth. Probes can function on Venus' surface for only a few hours at most. Mars holds our greatest hopes. This red planet features dried riverbeds and polar ice caps, indicating it once possessed liquid water and a thicker atmosphere. Today, Mars has a thin atmosphere and a cold, dry surface, with average temperatures around minus 60 degrees Celsius. Mars hosts Olympus Mons, the tallest volcano in the solar system, rising over 21,000 meters, more than twice the height of Mount Everest. It also hosts Valles Marineris, a vast canyon system stretching over 4,000 kilometers. Jupiter is the largest gas giant in the solar system, possessing a mass 2.5 times that of all other planets combined. Its most distinctive feature is the Great Red Spot, a massive storm system that has persisted for centuries, large enough to contain 2 to 3 Earths. Jupiter possesses a powerful magnetic field and radiation belts, along with a faint ring system composed of dust and rock particles. Currently, 95 moons orbit Jupiter, with the 4 largest known as the Galilean moons, discovered by Galileo in 1610. Saturn is renowned for its spectacular rings, primarily composed of ice particles and rock fragments. Only tens of meters thick, yet extending tens of thousands of kilometers above Saturn. The complex ring structure contains thousands of distinct bands. Gaps and wave patterns indicate moons influencing the distribution of ring material. Saturn's density is lower than water. If a sufficiently large ocean existed, it would float on the surface. Titan, Saturn's largest moon, possesses a thick atmosphere and a liquid methane cycle. It is the only known celestial body beyond Earth with stable liquid on its surface. Uranus and Neptune are ice giants. Their atmospheres contain abundant water, ammonia, and methane ice crystals. Uranus is unique for its extreme axial tilt. It rolls nearly flat on its orbital plane, resulting in highly unusual seasonal changes. Neptune holds the record for the highest wind speeds in the solar system, with storm speeds reaching 2,100 kilometers per hour. Its most prominent feature is the Great Dark Spot, a storm system comparable in size to Earth. Though now faded, new storms periodically form. In the distant Kuiper Belt, Pluto and other icy bodies form the outer reaches of the solar system. These celestial bodies preserve primordial information from the solar system's early formation, offering crucial clues for understanding planetary development. Beyond the 8 planets, the solar system hosts numerous satellites and minor celestial bodies, each narrating its own cosmic tale. As Earth's sole natural satellite, the Moon profoundly shapes our planet's environment. Its gravitational pull generates Earth's tides, and these tidal forces gradually slow our planet's rotation. Each day is lengthening at an extremely slow pace. The lunar surface is covered in thick dust known as regolith, and dotted with countless impact craters. The youngest craters still bear distinct ray patterns, while the oldest have been obliterated by subsequent impacts and are barely discernible. The Moon is drifting away from Earth at a rate of 3.8 centimeters per year, a pace comparable to the growth of human fingernails. Jupiter's satellite system resembles a miniature solar system. Io, Jupiter's largest moon, is the most volcanically active body in the solar system. Its surface hosts hundreds of active volcanoes, constantly erupting sulfur and sulfur dioxide into space. Europa, Jupiter's second-largest moon, is entirely encased in ice. Beneath this ice may lie a global ocean of liquid water, possibly exceeding the combined volume of all Earth's oceans. Whether life exists within this dark ocean is a primary objective for future exploration missions. Saturn's moon, Titan, is the only satellite in the solar system with a dense atmosphere, primarily composed of nitrogen, similar to Earth's early atmosphere. Its surface features lakes and rivers of liquid methane and ethane, and may even experience methane rain, forming a hydrocarbon cycle analogous to Earth's water cycle. Enceladus, though smaller in size, emits massive plumes of water ice particles from it. These plumes contain organic molecules, suggesting its subsurface ocean may harbor conditions suitable for life. The asteroid belt lies between the orbits of Mars and Jupiter, where millions of rocky celestial bodies orbit the Sun. The largest series, now classified as a dwarf planet, measures approximately 940 kilometers in diameter. These asteroids are remnants from the solar system's formation era. Disturbed by Jupiter's gravitational influence, they failed to coalesce into planets, preserving information from the solar system's birth 4.6 billion years ago. Comets typically originate from the more distant Oort cloud. When they occasionally enter the inner solar system, solar heat causes their icy cores to sublimate, forming spectacular cometary tails. These tails always point away from the Sun, driven by solar wind and radiation pressure. The famous Halley's Comet returns every 76 years. Its next appearance in Earth's night sky will be in 2061. Studying comets helps reveal the early chemical composition of the solar system, as these icy bodies preserve primordial material. The life cycle of stars spans millions to trillions of years. Their birth and death shape the face of the universe. Stars are born within vast molecular clouds, composed primarily of hydrogen molecules and interstellar dust. When disturbed by events like supernova explosions or galaxy collisions, certain regions within these clouds begin to collapse under gravity, As the collapse progresses, the cloud begins to spin and forms a disk-like structure. A protostar forms at the center, while surrounding material may coalesce into planetary systems. Newborn stars embark on distinct evolutionary paths based on their mass. The least massive red dwarfs can live for trillions of years, far longer than the current age of the universe. They slowly burn hydrogen fuel, glowing dim red with low surface temperatures. Our Sun belongs to the yellow dwarf category, with a lifespan of approximately 10 billion years. It currently resides in its middle age. More massive stars have considerably shorter lifespans, some existing for only millions of years, yet their existence is crucial to the cosmos. When a star's core hydrogen is depleted, the core contracts, increasing temperature and pressure, igniting carbon and oxygen fusion. The outer layers expand and cool, transforming the star into a red giant. For medium-mass stars like our Sun, they eventually eject their outer layers to form planetary nebulae, while the core collapses into an Earth-sized white dwarf. White dwarfs cease nuclear fusion, relying on electron degeneracy pressure to resist gravity. They will gradually cool and dim over the next 10 billion years. For more massive stars, the evolutionary process is far more dramatic. They sequentially fuse heavier elements, such as neon, magnesium, and silicon, until iron is formed. Iron fusion no longer releases energy, but instead requires energy input, causing the core to suddenly lose its support. Within less than a second, it collapses completely, triggering a supernova explosion. This explosion is extremely bright, sometimes even briefly outshining the entire galaxy. The supernova explosion scatters the heavy elements synthesized by the star into space, providing raw materials for the formation of new generations of stars and planets. Elements essential for life, such as carbon, oxygen, and iron, all originate from the remnants of these ancient stars. If the residual mass in the core is sufficiently large, it will continue collapsing into a neutron star. This celestial body possesses extreme density. A single teaspoon of its matter weighs billions of tons. Neutron stars typically spin at high speeds, and some emit regular pulsed signals known as pulsars. The cores of the most massive stars collapse into black holes, regions of such intense gravity that not even light can escape their pull. The dust and gas left behind after a supernova eventually coalesce into new molecular clouds over eons, initiating another cycle of stellar birth. Thus, matter in the universe endlessly recycles. The Milky Way is the galaxy we inhabit. It contains between 200 billion and 400 billion stars. It is a typical spiral galaxy, with a diameter of approximately 100,000 light years. The solar system is located on one of the Milky Way's spiral arms, about 27,000 light years from the galactic center. It orbits the galactic core at a speed of 220 kilometers per second, taking 230 million years to complete one revolution. At the Milky Way's core lies a supermassive black hole, Sagittarius A*, with a mass approximately 4 million times that of the Sun. Though relatively quiet at present, it occasionally devours nearby stars or gas clouds, triggering intense bursts of radiation. The Milky Way does not exist in isolation. It belongs to the local group, a cluster containing over 50 galaxies. The largest among them is the Andromeda Galaxy, which is approaching us at 110 kilometers per second. In about 4 billion years, it will collide with the Milky Way. However, the vast distances between stars make the probability of direct stellar collisions extremely low. The two galaxies will merge into a larger elliptical galaxy. The distribution of galaxies in the universe is not random. They form vast filamentary structures, with vast cosmic voids at their centers. This structure resembles a sponge or neural network. On the largest scales, the universe exhibits uniformity and isotropy. This means that no matter which direction you observe, the universe appears fundamentally the same on large scales. The discovery of the cosmic microwave background radiation provides strong evidence for the Big Bang theory. This is the lingering glow from the universe's early fiery state. After 13.8 billion years of expansion, it has cooled to an absolute temperature of 2.7 degrees Celsius. Minor temperature fluctuations reflect density variations in the early universe. These tiny inhomogeneities gradually amplified under gravitational forces, ultimately forming the galaxies and clusters we observe today. Dark matter is a substance that neither emits nor absorbs light, detectable only through its gravitational effects. It plays a crucial role in galaxy formation and evolution. Without dark matter's gravitational binding, galaxies would spin apart at their rotational speeds. Dark energy remains an even more mysterious force, seemingly uniformly distributed throughout space, exerting a repulsive gravitational pull that accelerates the universe's expansion. Ordinary matter constitutes only 5% of the universe's total mass energy. Dark matter accounts for 27%, and dark energy for 60%. We still know very little about the nature of the latter two. Modern cosmology seeks to answer fundamental questions about the origin and destiny of the universe. The Big Bang theory posits that the universe was born 13.8 billion years ago from an extremely hot and dense. In its initial moments, the universe underwent a phase of rapid expansion, growing by several orders of magnitude in an instant. This explains why the universe is so remarkably flat and uniform. As the expanding universe gradually cooled, energy began transforming into fundamental particles. Within the first 3 minutes, light elements like hydrogen and helium formed. After 380,000 years, the universe became transparent. Photons began propagating freely, forming today's cosmic microwave background. The first generation of stars began forming hundreds of millions of years later. Massive and short-lived, they enriched the interstellar medium with heavy elements through supernova explosions. Galaxy formation is a gradual process. Small structures form first, then merge to grow into large galaxies. Our solar system formed approximately 4.6 billion years ago, during the universe's middle age. Regarding the ultimate fate of the cosmos, 3 primary scenarios are currently proposed. If dark energy's repulsive force remains constant or intensifies, the universe will continue accelerating expansion. All galaxies will eventually recede beyond each other's event horizons. The cosmos will grow increasingly dark and cold. If dark energy decays over time, gravity may reassert dominance, causing cosmic contraction, potentially culminating in a big crunch. Another possibility is that our universe is merely one among many in a multiverse. Other universes may operate under entirely different physical laws. Theories like string theory, which attempt to unify quantum mechanics and gravity, predict the existence of extra dimensions. However, these remain unverifiable through experimentation. The search for a theory of everything continues, hoping to ultimately explain all fundamental forces and particles in the universe. It wasn't until 1995 that astronomers confirmed the discovery of the first exoplanet. Today, over 5,000 exoplanets are known to exist. The diversity of these worlds is astonishing. Some have orbital periods of just a few hours, while others take tens of thousands of years. The primary methods for detecting exoplanets include the transit method and the radial velocity method. The transit method measures the slight dip in brightness when a planet passes in front of its star. The radial velocity method, meanwhile, detects the Doppler shift in a star's spectrum to infer the star's slight motion caused by planetary gravity. The Kepler Space Telescope discovered thousands of exoplanet candidates by continuously monitoring a fixed patch of sky, many of which lie within the habitable zone. This region features moderate temperatures where liquid water may exist. Around red dwarf stars, the habitable zone is very close to the star, potentially causing planets to become tidally locked one side, perpetually facing the star, while the opposite side remains perpetually dark. Life in such environments may need to adapt to extreme temperature fluctuations. Moons orbiting gas giants may also harbor conditions suitable for life, such as the subsurface oceans of Europa and Enceladus. Though lacking sunlight, these environments may possess hydrothermal vents providing energy, similar to Earth's deep-sea hydrothermal ecosystems. The Drake equation attempts to estimate the number of intelligent civilizations potentially existing in the Milky Way. Factors considered include the star formation rate and the proportion of stars with planetary systems, the number of habitable planets, and the probability of life emerging. Although the values assigned to each factor carry significant uncertainty, the formula itself provides a systematic framework for addressing this question. The ECT program continues its search for signals from extraterrestrial civilizations. While no definitive discoveries have been made to date, the scope and sensitivity of the search are continually expanding. Even the discovery of the simplest extraterrestrial life would fundamentally transform our understanding of life's distribution across the cosmos. Astronomy is an observational science. We cannot directly interact with our subjects of study. We can only analyze the radiation they emit. Visible light constitutes only a small portion of the electromagnetic spectrum. Observations across different wavelengths reveal distinct cosmic phenomena. Radio telescopes detect cold gas clouds and the cosmic microwave background. Infrared telescopes penetrate dust to observe star-forming regions. X-rays and gamma rays originate from high-energy processes, such as black hole accretion and neutron star collisions. Modern telescopes grow increasingly powerful. The infrared capabilities of the James Webb Space Telescope enable us to study the earliest galaxy formation. 30-meter class ground-based telescopes are under construction, promising unprecedented resolution and light-gathering power. Multi-messenger astronomy combines diverse data sources, such as gravitational waves, neutrinos, and electromagnetic radiation, offering novel perspectives on cosmic events. The 2017 detection of gravitational waves from a binary neutron-star merger, correlated with signals in the electromagnetic spectrum, confirmed the formation mechanism of heavy elements like gold and platinum. According to Einstein's theory of relativity, the passage of time is not absolute, but depends on the state of motion and gravitational field strength. Global positioning systems must account for relativistic effects. Otherwise, daily errors would accumulate to several kilometers, theoretically traveling near the speed of light. Time dilation would cause astronauts to experience a shorter duration, but accelerating to such speeds requires immense energy and may present insurmountable technical obstacles. Concepts like wormholes and warp drive are mathematically possible, but require exotic matter with negative energy. These remain within the realm of theoretical exploration. The observable universe is limited by the speed of light. We can see celestial bodies up to 46.5 billion light-years away. Their light has traveled immense distances to reach us. What we see is their past state, not their present condition. Certain regions of the universe expand faster than light, remaining forever beyond our horizon. Light from these areas will never reach Earth. Now let us conclude this cosmic journey and return to this tranquil night. Together we have traversed vast space-time, from our familiar solar system to distant galaxies and cosmic frontiers. We witnessed stellar births and deaths, explored planetary diversity and mysteries, contemplated the universe's origins and fate. These insights reveal Earth's precious uniqueness in the cosmos. Each of us is composed of stellar matter and share a profound connection with this cosmos. The immensity of the universe reminds us that our daily worries and troubles seem so small and fleeting against the backdrop of cosmic history spanning billions of years. May this realization bring you inner peace. The darkness of the universe is not emptiness, but a tranquil canvas brimming with possibility, just as the night's darkness soothes weary souls. Now take a few deep breaths. Feel your body touching the bed. Let the cosmic imagery fade from your mind, leaving only profound stillness. May these tales of the stars lull you to sleep, guiding you into peaceful, serene dreams. Good night, my dear stargazer. May tomorrow's sunlight bring you renewed hope and strength. If you enjoyed this journey, please subscribe to our channel. Share this starry sky with more souls seeking tranquility.